So yeah, this topic is highly relevant to the previous topic, but I'm more focusing on the diffusional growth process in the ice crystal and droplets in mixed phase clouds. So clouds are key components in controlling and modifying the weather and the climate. But representing clouds in the model accurately is always challenging. So in the atmospheric world, the models, and including other types of model not related to atmospheric, the models have their own limitation in resolving a certain range of size scales. So in weather and climate model that resolve the continental scale or even global scales, because of their coarse resolutions. So for the grid spacing, it's usually several kilometers up to hundreds of kilometers. The models heavily rely on the subgrid parameterization to represent the cloud structure, cloud motions, and their microphysics processes related to cloud particles. So we have a parameterization squared problem in this kind of model. And for high resolution model, such as LES, it can resolve the cloud scale motions, but for the microphysics processes, it still depends on some parameterizations in their subgrid scales. So in order to explicitly resolve the process that related to the flow that down to cosmograph length scales, we really need to have a high ultrafine resolution model such as the DNS to resolve the motion of individual aerosol, droplet, and ice crystals and how they interact with the turbulence in the clouds. So in this model, the DNS in our model can resolve the velocity field and the temperature and moisture of the scales down to cosmograph length scale, and it also simulates the motion of Lagrangian particles and the growth of the particles by diffusional process that is affected by turbulence motion. So this model is commonly used in to study the warm cloud microphysics that usually don't have ice particles in it. But as the previous talk has studied, they also use that to study the ice microphysics process. But so far, we didn't find much study in the mixed phase where the droplet and ice talk to each other in the same environment. So this is the motivation of my study to include the ice processes into the DNS model. And so here listed the objectives of this presentation is first to present the mixed phase DNS that we developed, and then to demonstrate its model capability to study the interactions between ice, droplet, and the turbulence at their native microscales. And lastly, we want to use this tool to provide insights on how model can better represent the subgrid scales processes using our output, and ultimately we want to use these results to improve the cloud and precipitation prediction. Of course, that's a long way to go, but it's good to start from the fundamental. So in this model framework, it tracks the motion of individual cloud particles, including the ice and the droplets, and the turbulent fluctuation of temperature and water vapor fields are well resolved too. So we are able to study the impact of the thermodynamics and turbulence with the cloud microphysics. So with this tool, we can provide a more quantitative and controllable approach to study the mixed phase clouds. So here shows the left one is the 3D animation of the particles the right side is the horizontal snapshot of how droplets and ice respond to this different vortex. Because in this experiment, we are trying to simulate the turbulence intensity that's equivalent to the stratocumulus environment. So the eddy dissipation rate here is relatively low. So we don't see a very obvious droplet inertial response to this vortex structure, and it's very well mixed in this case. So we use this tool to trying to apply it to different type of cloud processes. So this example that I'm presenting today is we are trying to use it to study the ice growth in the cloud top generating cells. So what is that? So it's a commonly seen small scale structures in different types of mixed phase clouds. For example, on the right panel, it shows the cloud radar reflectivity in the vertical profile from the snowy field campaign. So the generating cell is, sorry, the generating cell, where's the pointer? Okay. It's actually can be seen in these fuzzy structures with a high reflectivity values and the adjacent cloud areas. And below these structures, you can see the fall streaks, which is actually the precipitating particles, such as snow raindrops. So this generating cell structure is the key area where we can initiate precipitation in the winter orographic clouds. So that's a process that we want to figure out what is the role of this structure in the ice growth. And the flight measurements from the same field campaign shows that the inside the generating cell, we have a much higher concentration of drizzle particles than the outside generating cells. And we also found that the same thing applied to the ice particles. So because of the limitation of the instruments, we here only show the ice particles larger than 100 micron in diameter, but we expect that it's the same thing we can see for the smaller ice particles. And here we also show some differences in terms of the vertical velocity. We have a slightly stronger updraft inside the generating cell than the outside environment. So we want to find out how those three factors that can change the ice growth history in these two different environments. So we set up a series of numerical simulations using the flight measurements as our initial condition for our DNS, and we try to study these different inferential factors on the ice growth rate and glaciation rate of different cloud parcels, and we compared the results from the conditions that's inside and outside the generating cells to figure out what's the key element that can trigger the faster ice growth. So here shows some results. So the left one is from the high liquid water content environment. So by high liquid water content means we have about 100 per cc of droplets of about 10 micron radius to be started in the simulation, and we also have the ice number concentration much lower number concentration. It's around 1 per cc of ice starting from 0.1 micron, which is very tiny to be expected in the ice nucleation status. And we put those two type of particles into the model and to see how each respond to this well-mixed turbulent environment. And the top row shows the ice radius, the average ice radius, with different initial relative humidity as listed here. So we can see that the ice growth is slightly less dependent on this initial relative humidity. But if we look at the droplet radius, which we can see most of the cases, the droplet evaporate. So this is mainly because of the different equilibrium saturation rate of a saturation ratio of the ice and the droplet. So in the same relative humidity environment, ice tends to grow at the expense of the evaporation of droplets. So that's why we see a growth, the fast growth in ice and the quick evaporation of droplets. But if we look at the saturation ratio from the ice and from the water, we actually see that they reach steady states fairly quickly, around 20 seconds after the simulation started. So it's they converge to the same steady state point for all the cases. And this steady state is actually maintained by an unstable microphysical condition. As we can see, the ice keeps growing and droplet keeps evaporating. And if we look at a low liquid water content, which is more equivalent to the non-generating cell environment, we can see a more diverse growth history of ice particles, where it's highly dependent on the initial relative humidity, which is expected because within the lower humidity environment, we don't have enough liquid water droplet to replenish the water vapor field. So ice will grow much slower in a lower relative humidity, and they don't even grow in the lowest case where the supersaturation field, the saturation ratio is below 100% for both ice and water droplet. So here we only look at the mean state, so everything is averaged over the parcel. But how does this affect the particle size distribution, which is highly dependent on the local turbulent field? So we also look at the size distribution for droplet on the left and the ice on the right. So the x-axis is the time and y-axis is the radius of particle. And the number concentration of each particle size is showing in color scales. And we can see that in this case, it's with a relative humidity around, I think, 90%. So it's subsaturated for water and slightly supersaturated for ice. So ice can grow very efficiently. And you can see this mean radius is decreasing. So droplet overall is evaporating, but we can still see some of the the droplets keep growing with time, even though we are in the subsaturated environment for water. So another interesting feature is that initially all the droplet and the ice particles started with small dispersed, meaning they are single-sized particle to start with. So we don't have the collision in our, we turned off the collision in our model. So these expanding in the size range is mainly caused by the fluctuation of supersaturation field. So which is very interesting because the broadening effect is so large. Within about 1.5 minutes, we can see a very significant broadening in water droplets and also in ice. Ice is not so obvious because it's the y-axis range is larger, but it's actually also a very significant broadening. And the right-hand side animation shows the cross-section of the supersaturation field, and we can see overall, even if we have a supersaturated environment with respect to ice, we can see pockets of subsaturated environment, which can trigger instantaneous evaporation of ice for a very short period. But then when the particles go to the supersaturated environment, they will grow again. So that contributes to this highly broadening size distribution. So this comes to the summary of the part one, showing that Geratin cells, generally with a higher liquid water content and relative humidity, can provide an ideal environment for ice growth. And we also found that the small-scale turbulence actually can broaden the size spectrum. And this is very important because this broadened size spectrum with very large difference in sizes can trigger collection process of large particles with small particles. And the second part is shorter, so we also look into how vertical air motions affect the growth of particles. So we know that air keeps move up and down, and so we have in the Geratin cell is kind of circulation system. So we want to use some simplified mean air motions with time to simulate this circulation. So in the upper row, we simulated 4 different air motions for the inside Geratin cell environment, where we have mean updraft over time about 1 minute per second, and we have on the lower row is representing the non-Geratin cell environment with the mean over time updraft of 0 meter per second. So we just trying different oscillation patterns, and here shows the volume. Okay, the domain average of the liquid water content, ice water content, and the ice fraction, basically the ratio of ice water content over the total water content. And we see that it's the blue one shows the Geratin cell with different updraft environment. They are convergent to the same pattern, meaning that this small scale or high frequent updraft and downdraft don't have very efficient or effective impact on this total water content. And so the orange line shows the non-Geratin cell environment. So this pattern shows that the mean air motion is more important compared to this high frequent updraft and downdraft. And we can also see from the ice distribution, ice size distribution, and it's quite similar for those different oscillation, different mean outside and inside the Geratin cell case. So here's the summary of the second part, and we found that the mean updraft in this case is the dominating factor in determining the liquid water content, and the small scale oscillation plays the secondary role. So in our case here, in all the different oscillation simulations, we have sufficient liquid water to provide it for the ice growth. So in this condition, the ice growth is weakly sensitive to the mean updraft. But we expect that if we have a much lower liquid water content, then the ice growth will be very sensitive to these updraft patterns. So yeah, I think that's it. maybe like just showing here. So our ongoing research, we are trying to add the ice geometry information in our model to see more complicated patterns. Thank you.
Thank you very much. Very nice talk. I'm sure we'll have some questions. Yes, please.
Sisi, that was very interesting. In the first part, you were showing the broadening of the drop size distribution. And I think you were attributing that to turbulence. Yes, this plot here. And I wondered whether you are including the solute term in the droplet growth and whether you might have some Ostwald ripening there where the larger drops are able to survive and even grow. Smaller ones are evaporating.
Yeah, that's a good question. We actually had a solute term inside, so it's relatively small solute content. I think it's 0.1 micron. So probably the solute effect's not that important in this case.
Right,
and
at this point, they're probably too dilute, right? What are your drop concentrations?
It's 100 per cc.
Oh,
yeah, and
probably not.
We probably can see some ripening effect at a later part when we try the oscillation. Over here, we can see some when we have some strong oscillations happening. We see some slightly higher liquid water content, but it's not so obvious in this case because the solute term is not very big. So when we have like strong updraft, probably like the droplet with larger sizes can grow faster than the smaller one in that case.
Yeah, or maybe you're just providing enough cooling to generate, to sustain more liquid water.
Yeah, but it's like the mean updraft over time is the same for those lines, those blue lines, but it's just the oscillation amplitude is different for those cases. So yeah.
Sisi, I want to make sure I understand how things are coupled. So your droplets and particles don't have an effect back on the velocity field, right?
Yeah, there's no dynamic feedback to the flow, but they have thermodynamic feedback.
Right, that's what I was going to wonder. So so when you have evaporation, that feeds back into the vapor field and so on, and the other way around too, right?
Yes, we have the two-way coupling of the thermodynamics.
Yes.
Yeah, that will feed back to the supersaturation fluctuation as well when ice grows. So it could have some strong feedback for the ice growth, but not from the droplet evaporation.
Yes.
Yeah.
All right. Yes, please.
Hi, it's Emily from Caltech again. Nice work. I was curious, if you were to have now, say, like a subgrid scale model for supersaturation fluctuations or vertical velocity fluctuations, do you have enough results here that you could directly translate that into like a microphysical impact in a larger scale model?
Yeah, that's a good question that I'm constantly asking myself as well. So for now, the shortest answer is no, but the information here we provides some insights on how to simplify the parameterization scale, parameterization schemes. For example, here we found that the oscillation is not so critical when we have like a mean updraft or mean downdraft. So when we parameterize it, probably we don't need to be paying attention so much on that oscillation.
Can I ask a quick follow-up? So what are you missing then before we can get to that point?
So that's because it's a very complicated system with radius dependent, the eddy dissipation rate dependent. So first step, we probably need to formulate impact of turbulence in terms of its intensity on the droplet growth equation. And for the subgrid scale model, even if we have information from the eddy dissipation rate, we still need to find a way to incorporate that into different grid box with different eddy dissipation rate, for example. So that can trigger some difficulty, but the difficulty is not from the DNS pilot, but how we put it in the LES or other models of larger scales. So even if we have a formula, probably there's some steps away to apply to that.
Good. Yes? Mm-hmm.
Yeah, hi, this is nice talk. Just wondering, could you remind me what is the ice number concentration in your simulation?
So in this case, it's 1 per cc. So
1 per cc, okay.
It's actually higher than the normal concentration in clouds, but yeah, we just want to see some simplified simulations.
Okay, yeah, because some of the observation you show, it's like 1 per liter. And in your simulation domain is 1 liter. So just wonder if you put like 1 ice particle in the simulation domain, can you see some like inhomogeneous in this original process? Like when there's droplets close to the ice particles, they will evaporate faster than others?
Yeah, we haven't really looked into that small scale region to see the dynamics, but I think from here we can see some intermittent phase intermittency structure that exists in very short time scale. That we still need to look into whether this short time scale intermittency has an impact on our microphysics as an average. But yeah, that's a very good question.
Thank you.
Yes, Michelle.
Yeah, very nice talk. Thank you so much. With a relative humidity greater than 1, I presume that this is a non-equilibrium process. Mm-hmm. And so is it obvious which limit we are talking about? Do we have a kinetic limit? Do we have a diffusion limit on the transport of moisture to and from the particles? Are you, at small particle size, I would expect that this would be a kinetic limit?
Can you
so in other words, do we have rate constants for the exchange, since you're not in equilibrium?
So you mean what is the equilibrium of the supersaturation field, or is that?
Yeah, I think in general, even if it's not supersaturated, are you always assuming some kind of an equilibrium?
Mm-hmm. Yeah. In this case, you can see that this equilibrium is there. This is because of the evaporation of droplet balanced the depositional growth of ice crystal in a way that it keeps the slightly subsaturated.
How is the rate described?
The rate of condensation.
Of exchange of the moisture to and from the particles.
That depends on the saturation ratio. So it's like, so the rate is actually a function of the total area of the particle surface. So that area is the R squared dt. So it's proportional to S. And so S is the saturation, so it's available water vapor in the air. So it's more available water, so it's faster the water vapor condensed to the surface of the particles. Yeah. That's.
Jeff, yes.
So this follows the prior question. Do you have a coupling of the fluid mechanics and to the transport rate from the surface? The shear flow and the relative velocity to give me a mass transfer rate?
On the droplet surface, it's not resolved in our case because the flow field is Eulerian. We have some limits of the grid resolution. It's of the same scale as Kolmogorov length scale. And then for the particles, is several micron in radius. So it's like much further smaller than the grid box of the turbulent model. And we assume that in each grid box, we have uniformly distributed relative humidity and temperature field. We have some assumption on the time scales of the phase relaxation time scales. We assume that droplet will condense in this uniform environment.
I see. So it's always deviation, thermodynamic variable deviations. Okay.
Yes, yes.
Have you been looking at homogeneous mixing or inhomogeneous mixing?
Yeah, that's a great question. That's what we are going to do, is to trying to incorporate the local inhomogeneity of the thermodynamic field. But for now, it's homogeneous. It's kind of homogeneous and adiabatic flow as well. And we don't have the entrainment of dry air to stir up the flow.
Okay, if there are no more questions, then I'd like to thank all of the speakers of this session again for